Hello everyone, welcome back to Chapter 3, Part 2. In the previous video, we defined the characteristics of what it is to be a vector. Specifically, our vector has to have a magnitude and angle, but we also learned in the previous video that in addition to describing a vector using magnitude and angle notation, which needs to be specified from a given axis, we can also have a vector that is described using its x and y components. And so what I have for vector A is a vector that is 5 meters long, and it is pointing at 30 degrees with respect to the x-axis. And so vector A would look something like this. Again, this is a rough sketch, and these sketches are fine as long as we're just using them to get a basic idea of what the vectors in the system look like, but we want to let the math do the real work for us. And then for vector B has components along the x and y directions, 3 and 4 specifically. And if we follow along those directions in the x and the y direction, then we will produce our vector B. And then we can figure out what the angle that vector B makes with the x-axis by combining the x and y components of our vector using the inverse tangent. And we can find the magnitude of our vector by using our magnitude mantra, which is the square root of the sum of the squares. And as it turns out, the magnitude of vector B is also 5 meters. What I've used here is the 3, 4, 5 right triangle combination. However, for vector A, even though vector A has a magnitude of 5, it will not have the same x and y components as vector B, and that is because vector A is sitting at a different angle. I'll call that angle phi. It's sitting at a different angle from what vector B is sitting at. And if we plug in the values from vector B into our calculator to figure out what that angle is, we need inverse tangent of 4/3. Whoops, I don't think I entered that into my calculator correctly. One more moment. Inverse tangent of 4/3 is, oops, sorry, that should have been theta, not 0. 53 degrees. So quite a different angle between the two, even though they had the same magnitudes. And we could easily find the components of vector A by combining the magnitude of our vector along with the angle using the appropriate trig functions. The x component of vector A is the leg that is adjacent to our angle phi, so that would be our magnitude sine of our angle, or 2.5. I'm sorry, that is really wrong. That is the side adjacent, so that should be cosine. Alright, so that should be about, what is it, 4.33. We'll double check that on my calculator. Yep. And then the y component, that will use the sine of the angle, and that would be 2.5. All right, so the big thing to take away from the previous video was that for any vector given in magnitude and angle notation, we should be able to convert that to component form, and obviously if we can convert one direction in the math, we should be able to convert back. And so that's what we've done here with this little review set of vectors. But moving on with today's discussion, what we want to do now is see what happens if we have more than one vector in a given system. And so this is what we're going to call vector addition. And once we get the vector addition figured out, then we will discuss vector subtraction. And one good example of vector addition is if you're going to be giving someone directions. So let's take ourselves maybe a couple of roads. And we want to get from point A to point B. And if you need to, you can put in some extra roads wherever you need them to be. But we want to get from A to B, and we'll say that each segment of road is 1 mile or 1 block. And so to get from A to B, we have a couple of choices as to the route that we can take. And the first route could be that we go east 1 block, north a block, east a block, north 2 blocks, and then east a block. And that would get us to point B. Another possible route that we could take would be going north a block, and then east, and then east, and then north, and then north, and then east. So there are other possible routes, but given the layout of this example, any other route that we take would require some form of backtracking in the route. For instance, if we went all the way east and then north, well, the road doesn't continue, so we'd have to backtrack a little bit, and that's not really an efficient route. So we'll focus on the first 2 routes that we took. And if you notice, we're still getting from point A to point B, even though we took different routes. But if we go through and we actually tally all of the different directions that we've taken, for the first route, we had, we had 1 block to the east, 2 blocks to the east, 3 blocks to the east, along with 1 block north, 2 blocks north, 3 blocks north. For the second route, we had, we'll switch over to that color, 1 block east, 2 blocks east, 3 blocks east, 1 block north, 2 blocks north, 3 blocks north. And so if we were to completely discount the fact that the roads don't necessarily go there, but if we just added together 3 north, 1, 2, 3, and 3 east, that would still get us from point A to point B. And so each one of these individual segments can be considered a vector in and of themselves. So if we take the blue route there, every time I traveled, there was a specific direction along with magnitude that had to be traveled. And what we're doing essentially is we're adding vectors together. And the number one rule for vector addition is that vectors are added head to tail. And so that's exactly what we're seeing happen here. I'm going to get rid of the green route here if I can, along with the purple route. Just leave the blue route. Okay. So we've got our blue route, and every time I put down a vector, so this first vector that was laid down, the second vector had its tail added to the head of the first vector. The third vector has its tail added to the head of the second vector, and so on and so forth, until we finally get to our endpoint at B. But let's consider rearranging all of these individual pieces back into the purple route. The purple route would seem by far the most efficient, because I would only have to travel north 3 and east 3, and then I would be done. Problem is the roads don't go that way, but now, since we're in a physics class, we can make lots of assumptions. Let's assume that we're a bird and we want to fly from point A to point B. Well, if we were going to do that, then we would just fly in a straight line from A to B, but that line has just become the hypotenuse of a right triangle that has been formed using all of the individual x and y values of the vectors in the system. No matter how I arrange all of these north and east bound vector combinations, I'm always going to end up 3 blocks north and 3 blocks east. And so I have produced a right triangle of side legs 3 and 3. And I would like to know, what is the hypotenuse? What have I produced by adding all of these vectors together? And so we're gonna call the result of this vector addition the resultant. So the resultant, this is the vector result of addition. So when we add vectors together, the resultant will be drawn from our starting point. So we started right there at point A to our endpoint, point B. And we draw our resultant between points A and B. So this line right here, this is the result of adding together all of those individual vectors that we used in traveling from point A to point B. But as we said, it really doesn't matter how we get from point A to point B, even if we took one of these backtrack routes. I could have gone over 1, 2, 3 to the east, up 1, 2, but then I'd have to backtrack 1 in the east. I'd go up 1 more north, and then I'd go over 1 more to the east. And what happens? Well, that backtracking actually ends up canceling out. But I'm still going from point A to point B. I still have a final resultant vector that is exactly the same as for any other route that I would take. And so the way we're going to find the magnitude of that resultant is we need to know what are the x and y components of that resultant vector. And we can already see what those are. They are the side legs of the right triangle that we made. Again, no matter how we add up all of the vector components along the x direction, we always get 3 in the x for our final displacement. No matter how we add together the y vectors, we always end up with a final displacement of 3 in the y direction. And so having a displacement of 3 in the x and a displacement of 3 in the y, that's one way of describing vector r. No matter which path I take, I always end up traveling 3 to the east and 3 to the north. But now I want the magnitude. And so by now our brains should be chanting the magnitude mantra. We want the square root of the sum of the squares. Since we've got 2 components that are the same values, I'm going to end up with root 18. And this is now magnitude. So root 18, what is root 18 going to be? So that's, 3 square roots of 2. But I'll just plug this into my calculator, get a decimal value, 4.24. And I didn't specify exactly what the units were, I just said blocks. So we've essentially traveled about 4 1/4 blocks in getting from point A to point B. Alright, well if that's all it takes, if all we have to do is add together all the vectors head to tail, that's not a big problem. But what do we do if one of those vectors, or maybe even more than one of those vectors, happens to be at some odd angle? Let's define a couple of new vectors here. We'll take vector A. This will be 5 meters at 0 degrees with respect to the positive x-axis. So this vector is just lying on the x-axis. I'll go ahead and draw it just so we can see. And I should probably put some marks in here. 1, 2, 3, 4, 5. So there's vector A. Vector B will be 8 meters at, we'll do 90 degrees with respect to the positive x-axis. So this means that vector B is actually pointing along, I'm sorry, did I say y-axis or x-axis? We're 90 degrees with respect to the x-axis. But in measuring that 90 degrees, this means that vector B is actually pointing along the y-axis. And I should draw this more to scale. This is why I said we're not going to be relying too heavily on the sketching. But 1, 2, 3, 4, 5, 6, 7, 8. So that's what vector B is going to look like. 8. We'll just say that everything is in meters. And then we got one more vector, which we will call vector C. And vector C is 10 meters long at 60 degrees with respect to the positive y-axis. Okay, so what does that mean? Well, once again, I'll make a sketch so that I can see what the vector looks like. Why did I put an X? Why didn't I put an X there? It should be an X. Vector C is 10 meters long, and it has to be measured 60 degrees from the positive y-axis. Well, 60 degrees from the positive y-axis would be right about there. And so I would have to draw vector C like so. Should have drawn it so that it matches the other colors there. Alright, well there's the 3 vectors that we have in this system. And what I want to do now is add them all together. We want to take vector A plus vector B plus vector C, and we are going to produce what we are calling now the resultant vector. What I want to know, first of all, what are the x and y components of that resultant vector, and then once we know those, I want the magnitude and angle for that resultant vector. Now here's where we're going to really distinguish between using the graphs and using the math. We've already seen up above that it doesn't matter the order in which we add all of these vectors together. And as it turns out, vector addition does follow the commutative and associative rules of algebra. And so A plus B plus C would be the same as B plus C plus A, or really any other arrangement that you can think of. And so it doesn't matter what order we combine these vectors, we're still going to get to the same end point. So for our purposes, let's take these 3 vectors and we will add them together on a fresh xy axis. I'll go ahead and just use vector A first, since it's the first one in line. So vector A has to be 5 meters along the x-axis, which is going to bring us right out there. So there's vector A. Then I have to add to the head of vector A the tail of vector B. Well, really what I'm going to do is I'm just going to take vector B, I'm going to pick it up, and I'm going to stick it right on the head of vector A. And so when I do that, I get vector B, which goes up 1, 2, 3, 4, 5, 6, 7, 8, which would be right about there. So right now I have vector A plus vector B. And then I have to add vector C. So I have to take vector C And I have to add that to the head of vector B. And just like what happened with vector B, I'm going to take vector C, I'll just pick it up and I'll bring it over and I'll set it right on the tip of vector B. Now some people have a little bit of issue with knowing how they want to draw this vector addition and exactly where the next vector should be pointing. So my recommendation is if you're struggling with trying to draw the vector addition, just place a tiny XY axis right at the point where you're trying to draw the next vector in line. And you remember that vector C had to be 60 degrees with respect to the Y axis. So I'm gonna take that picture for vector C, and I'm just going to duplicate it right where that miniature XY axis is sitting at. But this has to be approximately 10 meters long, so we'll come out here about 10 meters or so. We'll call that vector C. And so that's what my picture is going to look like. Now I'm not really sure exactly what 10 meters is going to look like on this picture. It might even be a little bit longer. And this is why sketching these graphs is really not that great of an idea, because right now if I were to draw the resultant vector, our resultant vector has to be drawn from the start point to the end point. My drawing would suggest that the resultant vector is a quadrant 2 vector, because I have a small x component that looks like it's pointing in the negative, and I have a very large y component that looks like it's pointing positive. Now that could very likely be true, but I don't know for sure yet. The only way that I can know for sure is if I can take this vector addition and simplify it to consider that the x component of my resultant vector comes from the combination of the x components of the three vectors that were added together. Likewise, the y component of the resultant vector is the result of combining the y components of the three vectors. And so if I can find the x and y components of these three vectors, I can very easily add those together and find the components of vector r. And in fact, that's the first thing that we're tasked with doing, is finding those components. And once we have the components, we can very easily find the magnitude and the angle. And so I'm gonna say this now, and I'll probably end up repeating myself multiple times, but when working with vectors, it is far more useful to have the components of the vector available. The magnitude and angle, those can be converted to components, but trying to work just with magnitude and angle can be very frustrating, and it can be very misleading at times. So what we need to do is take a moment and convert our three vectors, which are in magnitude and angle format, into component forms. For vector A, we know that vector A is 5 meters long, and it's pointing 0 degrees with respect to the x-axis. Well, if vector A is lying on the x-axis, that means that all of vector A has to be x. Or, another way of saying that is that the y component of vector A has to be 0. And so plugging those values in, we have 5 and 0. Does that work out? And looking at the picture, yeah, that works out. That's not a problem. Does that work with all of the trig and the Pythagorean theorem? Well, if you plug those two components into a Pythagorean theorem, we get square root of the sum of the squares, but doing that, we just get the square root of 5 squared, which is 5, so yeah, that works. If you were to use your 0 angle, we have this 0 angle there with our trig functions. We have a magnitude of 5. A cosine of 0 would be 1 times 5 is 5. So yep, there's your x component. Your y component would be 5 sine of 0. That's 0. Yep, that's working. So all the math is there. All the trig is supporting what we have. But at this point, it should be pretty obvious as to what we have to work with, especially if the vector is sitting all in one direction. Likewise for vector B is all in the y direction, and so it will have a 0 x component, and that means everything else has to fit into the y-axis of positive 8. The only vector where we really have to do some work in deconstructing it is vector C. And vector C is technically pointing in the second quadrant, and so this means we will have an x component that is pointing in the negative direction and a y component that is pointing in the positive direction. So the pairing of the x and y respectively will be negative positive. And we said that the angle was 60 degrees from the y-axis. Okay, that's no big deal. We have a vector that is 10 meters long. It's 60 degrees from the y-axis, but that 60 degrees is not a part of that right triangle that I've just drawn. Not a problem. We also discussed this in the last chapter. We can take the difference in the 60 and the 90 degrees, and we can use the 30 degrees inside of that triangle to help us find out what the values of the individual components need to be. The only thing that we need to keep in the back of our mind is that that x component needs to be negative and that y component needs to be positive. The x component, that is the leg that is adjacent to our angle. So we have 10 cosine 30. Oops. 10 cosine 30. Our y component is the leg that is opposite the angle, that is 10 sine 30. And that's going to make for a positive 5, and I believe this is a negative 8.66, but I'll double check that on my calculator just to be sure. Yep. Okay, those two values we will now bring up here. 8.66 negative and 5. So those are the components of the 3 vectors. And now we have to add together all of those components. Well, the way I have this written, it would be super easy if we just dropped right down the columns, adding everything together. And when we do that, we will get the x and y components of our resultant vector. So for the x components, I have 5 plus 0 minus 8.66, which will result in a negative 3.66. For the y components, we have 0 plus 8 plus 5, which is 13. And now we're good to go. We have the components of that resultant vector, and now it looks like my graph was actually pretty accurate, because I did end up with negative x component and a fairly large y component in comparison. But now that we have those components, it's time to find the magnitude of our vector. So we need square root of the sum of the squares. Now one of our components is negative, and whenever we square something, whether it's positive or negative, the result is going to be positive. And that's going to be important when solving for any magnitude, because if you find yourself with a negative value inside the root, then you're going to get an imaginary solution. And with physics, we're talking about real-world problems and real-world situations. We don't have the luxury of an imaginary solution. So if you do find that you're taking the root of a negative number, stop, go back, check your work, because something somewhere went wrong. Alright, we have 3.66. We're going to square that. We'll add that to 13 squared. We will square root our sum, and so let's see here. I'm getting approximately 182. The square root of that is approximately 13.5. I don't need that root anymore. And since we were using meters for all of the units of our vectors, our resultant will also have units of meters. But now we need to figure out where it's pointing. Now again, we can go back up to the sketch that I made right over here, and we can say, well, it kind of looks like our resultant vector is a little bit past that 90-degree mark. Again, it's really not worth trying to guess what that angle is. We want to get an exact value, and we're going to get that exact value from the components. But now that vector r is over in the second quadrant here, how are we going to figure out that angle? Because if I try to solve for theta, I can see here that theta is bigger than 90 degrees. And everything that we've been working with in terms of these vector components requires us to use some kind of right triangle. So an alternative is that we can work with the components that we have, we have our x and y components, and they do form a right triangle with the vector itself, but maybe we would have to measure our angle with respect to a different axes. Instead of trying to measure from the positive x-axis, maybe we could measure from the negative x-axis. Well, we're going to let the trig do its job. I want to know what this angle phi is, and I can do that by taking the values of the x and y components and plug them into an inverse tangent expression. The tangent of angle phi would be opposite over adjacent, and so phi would have to be inverse tangent of our 13 over our 3.66. Now, if you put that into your calculator, 13 divided by a negative 3.66 is going to result in a negative 3.55. And then if we take the inverse tangent of that, we're going to get an angle that is negative 74.3 degrees. And we need to ask ourselves, does that make sense? Any negative angle measure has to be made in the clockwise direction. If I'm trying to measure from the x-axis over to where the vector is currently sitting, well, that's the counterclockwise direction. That's not the right direction. Plus, that's more than 90 degrees. That doesn't match up to the answer that we have right here. But if we were to start at the negative x-axis and measure to where our vector is sitting, does that look like it might be more close to that value of negative 74? And not only does that look pretty close to 74 degrees, but we're also measuring in the proper direction. This is actually the negative direction as measured from the negative x-axis. Now at this point, I know what you're probably thinking. You're probably thinking this looks way too complex for trying to figure out the angle that our vector is measured at. Isn't there an easier way to do this? And the answer to that is yes, there is. I want to show you that easier method right now. And that easier method goes back to where we left off in the previous video with the 4 quadrants and how our x and y components appear in those quadrants. For any vector in the first quadrant, both components will be positive. For any vector in the second quadrant, you're always going to have a negative x component and a positive y component. Oops, that should be negative. For third quadrant, both of your components are always going to be negative. And for fourth quadrant, you'll have a positive x and a negative y component. Now, the reason I bring this up is because for any vector, regardless of the quadrant that it's in, we have a tendency to get a little complacent with our math, and we say that the angle that the vector makes is equal to the inverse tangent of the y component of the vector divided by the x component of the vector. And there's nothing wrong with using that, but we have to be very careful with where we measure the angle from. There are a lot of different places where we can start measuring an angle, but we have to specify where that is in order for our answer to make sense. Up here, our answer only makes sense if we start by measuring from the negative x-axis. So how are we supposed to know? When do we measure from the positive x? When do we measure from the negative x? And the answer to that is going to be very, very, very simple. We just had a vector that was in quadrant 2. And here's the way it's going to work. Whatever you have in the denominator of your inverse tangent expression is the axes that you want to measure with respect to. Now we look at that and you say, well, it's x, so I have to measure from positive x. Well, that's only true if the value that you insert is positive. If you insert a negative x component into this expression, then you will need to measure from the negative x-axis. And so that's actually a very easy thing to keep in the back of our brains, is that whatever value ends up in the denominator, that component along with its sign, that is the axes that you need to measure with respect to. And so if we had some other vector, we'll say vector f, which has components -7, -12. Okay, right away we can tell that is a third quadrant vector because both of its components are negative. But now I want to find out what is the angle that this vector makes. So I'll take inverse tangent of y component over x component. Now those minus signs, they are going to factor out, but before you do that, look at what you have in the denominator. You have an x component that is negative, and so you will have to begin your angle measurements from the negative x-axis. We'll go ahead and plug the -12 over -7 into our calculator, along with the inverse tangent. And I am getting an angle that is approximately 60 degrees. And that did come out positive, just so you know. And it should, because we had two negatives in that quotient. But I'm getting a positive 60 degrees. Where do I have to start measuring that angle from? Well, since the denominator was a negative x component, I'm going to start measuring from the negative x-axis in the positive angle direction. And so this is what vector f is approximately going to look like. Now, if you were to sketch in the components of vector f, well, vector f has a negative x component and a negative y component. Does everything look like it's matching up? Yes, it does. Both components are negative. My vector is in the third quadrant, and I do have a positive 60-degree measure from that negative x-axis. Now, from time to time, your homework set may ask you to measure the angle of your vector with respect to the positive x-axis. Well, that shouldn't be a problem now that we know what the angle is with respect to the negative x-axis. If I want to measure the angle relationship of my vector with respect to positive x, well, all I have to do is add that extra 180 to my value, and I have my answer. So 180 plus the 60 is going to result in an angle of 240 degrees with respect to the x-axis. One little thing worth noting: when you are measuring an angle, technically you can measure the same angle from two different directions. So perhaps this first angle here, theta, is 120 degrees. What would the equivalent measure be if we went the other way? Well, that would be negative 240 degrees. Which one is right and which one is wrong? Well, they're both right. They're both valid forms of measuring the angle of that particular vector with respect to the x-axis. But in our online homework, the system is only going to accept one of those answers. So which one is it going to be? And in a lot of those homework questions, the system will tell you that only values between plus and minus 180 degrees are valid. So any angle that you enter has to be between positive and negative 180 degrees. And I look at that and I say, well, that's everything. What's the big deal? Well, the big deal is that you cannot cross that line. In any of the measures that you make for an angle, you cannot cross that line. If you do, Wiley will not accept your answer. So if you have a vector that is right here, and you want to measure the angle that that vector is sitting at, how are you going to measure it? Are you going to measure it using a positive angle notation or a negative angle notation? And in getting to that vector, if we measure from the positive axes, well, I would have to cross that forbidden line to get to the vector. And so Wiley would not accept that answer. But if I measured in the negative direction, I would get to that vector without crossing that forbidden line, and then Wiley would accept the answer. So do keep that in mind when you're figuring out your angles, because Wiley will almost exclusively want vector angles measured from the positive x-axis. That's not to say every now and then it might not ask for a different axes to measure things from, but probably 95% of the time this is where you're going to start your angle measures from. So we now know how we're going to add our vectors together. My screen does not want to zoom in for some reason. But we now know how to add these vectors together. Our best bet for any vector addition problem is to convert those vectors to component forms so that we can then add them together and get the components of our resultant. From there, we can find the magnitude and angle of our resultant using the trig. But now we have to consider vector subtraction. How are we going to subtract a vector? Let's go ahead and keep the three original vectors that we were using. We had vector A, vector B, and vector C. And we already know that the order in which we add our vectors together is not going to matter. I can add numbers together in any order. That's not going to change the end result because addition is commutative and associative. Unfortunately, subtraction is not. Subtraction does not follow the rules of the commutative and the associative, meaning I can't just take vector A minus B and expect that to equal vector B minus A. That doesn't work. Well, same thing is true for any combination of vectors where subtraction is involved. Well, before we jump into the vector subtraction, let's talk a little bit about multiplication of vectors. Specifically, I want to take, let's call this vector V, which has components 3 and 4. So this is everybody's favorite. It's the 3, 4, 5 triangle. Vector V will have a magnitude of 5. And we can draw this if we want. In fact, we will. 1, 2, 3. 1, 2, 3, 4. So there's vector V. What would happen if we took vector V and we multiplied it by the scalar value of 2? Well, multiplication is just a more efficient means of performing addition. And so if I took vector V and I added it to itself, well, V plus V is 2V, so I now have a resultant vector that has a length of 2V. So we have a resultant vector of 2V. But what are the x and y values of this new resultant vector? Well, I already know that for the individual vector V, we had an x component that was 3 units long, but that doesn't change just because we added an extra V. I just have to continue traveling out another 3 units. And so my resultant vector will have an x component that is twice the size of the individual x component. So my vector 2v has an x component which has to equal twice the original x component, or 6. Likewise, the y component of the resultant vector just has to be twice the value of the original y component, which was 4. So now it's 8. Does that mean that 2 times the value of vector v means that we now get 2 times the magnitude of vector v? Well, vector v, as we said, had a magnitude of 5, square root of the sum of the squares, 3 squared plus 4 squared, square root equals 5. Well, twice that value, twice that magnitude should be 10. Is that what we get if we plug in square root of the sum of the squares of our new components. And believe it or not, it actually works. 6 squared is 36, 8 squared is 64. You add them together, you get 100. Square root of 100 is 10. So it does in fact work. This scalar multiplication, not only does it work on the magnitude of the vector, but it carries through directly to every component of that vector. So now we can say that the components of vector 2v would just be 2 times the components of the original vector, 6 and 8. All right, so well, that's going to be true for any scalar multiple that we use, whether it's 2, 3, 10, 100, even with negative numbers. And that is where we're headed now, because when it comes to vector subtraction, we want to take one vector and subtract another vector from that first one. But what is a subtraction problem but just a simpler way of saying we want to add a negative? There is no difference between these two statements. We could say 5 minus 7, that's negative 2, but 5 plus a negative 7 is also negative 2. There is no difference in these statements. And because we already know how to perform vector addition, there's really no reason in trying to learn a new process for vector subtraction. We'll just do another addition problem. The only thing that we need to do is we need to figure out what is a negative vector going to look like. Well, we'll take the idea of our scalar multiplication, and let's see what happens. If I have vector b and vector a and vector c, so these were 5, 0, 0, 8, and then, let's see, I've forgotten what my values for vector c were, negative 8.66 and 5. So if these are all of my vectors, what would it take to turn one of these vectors into its negative counterpart? And if you think about a number on a number line, let's say we have the value positive 6. And if I take positive 6 and I multiply that by a negative 1, well, that turns it into a negative 6. If this were a vector of positive 6, and then I all of a sudden multiplied it by negative 1, well, what happens to the vector? It needs to turn around. It needs to flip. It needs to turn around by exactly 180 degrees. That's all we have to do. All we have to do is flip the vector over. And that can be done regardless of the type of vector. Remember, we had our vector that was 3, 4. Okay, well, that vector had component positive 3, positive 4. If I all of a sudden multiply that vector by a -1, that vector, I think we were calling this vector v. Well, let's take vector v and multiply it by a -1. What we do to one side, we have to do to the other. And we now have the vector -v, which has components -3, -4, -4. Where does vector -v point? Well, it points in exactly the opposite direction of what vector v points. And we can actually prove that to ourselves by traveling backwards -3 and then down -4, and we get exactly where we need to be. So this is a very, very efficient way of taking a vector and producing its negative counterpart simply by carrying a negative sign through the math. The vector -a would be -5i hat plus 0. Okay, 0, 0, there's nothing there, so 0 can't be positive or negative. The vector -b will be 0 minus 8. And the vector -c will be positive 8.66. So if I apply a negative to a negative, I get a positive, but then we'll get a -5j hat. So those are my negative counterparts for these vectors. And now we need to figure out what kind of vector subtraction problem we want to do. So I'm going to go back up to the vectors that we had available to us. And let's see, let's just try, we'll do vector a minus b minus c. Vector a minus b minus c. So I want a minus b minus c. So very quickly, we do not do vector subtraction in our class. We add negative vectors because it is no different. We want to take vector a, we want to add it to the vector -b, and then we want to add that to the vector -c. Now the reason I came back up here, these are the same values that we had below, but I want to show you just how quick this is going to be. This vector addition is going to provide us with some resultant vector. And I want to know what that resultant is. This resultant has x and y components. Now in the previous case, we just went right down the columns and we added everything together. Well, I can't do that right now because I don't have the proper vectors. I need the vector -b and I need the vector -c. Well, I can do that really quick. All I have to do is slap a minus sign in front of the b and then carry it through to all of the components on the inside. So now I have 0 minus 8j hat. That is the vector -b. That's exactly what we have down here. See, there's the vector -b. Likewise, we're going to slap a minus sign in front of vector c, and we're going to carry that minus sign through to all the components. 2 negatives makes a positive, 8.66. And we get a -5. Now we can add all of these vectors together, and we can just drop right down the columns the same way we did before. We have 5 plus 0 plus 8.66. That gives us a 13.66. For the y components, we have 0, minus 8, minus 5, so that is a negative 13. And we now have the components of our new resultant vector. Perhaps we should distinguish between these. We do have a different combination of vectors going on, so we will get a different resultant vector. And now that we have the components of our new resultant vector, we can take those and we can find the magnitude of this resultant, square root of the sum of the squares, and we can find the angle that this resultant points at using our inverse tangent. And if you didn't catch on, at no point during this particular vector combination problem did I need to draw anything. I did not have to sketch the vector negative b, I didn't sketch the vector negative c. All I did was I allowed the math to do its work. And from this point, I can now allow pretty much any combination of these vectors that I want. If I want to take the combination vector c plus, we'll do the vector c minus a plus b. So how would we do that? Well, we would need the vector positive a. We would have to add to that the vector, sorry, I misspoke on that. We need the vector positive c. We're going to add to that the vector negative a, and then we add to that the vector b. Well, I'm pretty much ready to go. I'm going to get rid of the second set of values here. We'll just focus on what we have over to the right there. I already have vector c, it's good to go. I already have vector b, it's good to go. The only thing that has to change is vector a. So I will slap a minus sign to the front of vector a. I will carry that through the components. Nothing really changes except for the negative 5. And now I'm ready to add everything together. I have vector negative a, I have vector positive b, I have vector positive c. They will add together to produce some resultant vector which has components, looks like negative 13.66 and 13. Is that the same thing that we had before? Is that the same thing that we had up there? Nope. The signs are backwards. That's interesting. So we went from having vector a minus b minus c to essentially, what do we have up here? We have the vector negative a. We have positive b, positive c. Well, as far as these two combinations go, this top line right here is just the negative version of that combination. And so what would happen if we put a minus sign in front of R3? Well, we would get that previous combination of R2 that we had up at the top. So it is possible to manipulate the signs on these vector addition, vector subtraction problems, that you can actually produce opposite vectors of one another, and that's exactly what we did here. Now I believe that'll be enough for one video for today, but we've now seen how vectors can be added together. Again, I will say that vector components are the way to go. If you are given vectors that are in magnitude and angle format and you have to add them together, please take the time, break them up into components. It is well worth the effort. And then if you have to put those components back together to form magnitude and angle, you certainly can, but it's not necessary. If I were to ask for the combination of vector A minus B minus C, and I did not specify how I wanted the vector to be expressed, there's absolutely nothing wrong with expressing your vector in component form. In fact, I actually prefer vector components above anything else. Alright, we'll be back with at least one more video after this. We want to look at a few more vector combination problems in terms of the math, and then we want to look at some more situations where we have vector multiplication. So far we've only had scalar multiplication with vectors, but now we need to see what happens when we take the product of two vectors. Because right now really the only multiplication that we know of is algebraic multiplication. How are the directions of these vectors going to combine in a multiplication process? And that's what we need to figure out. So we'll see you at the next video.